Conservation of energy is a big topic in mechanics and sort of discusses that energy is neither created or destroyed, but it's just transferred from one form to the other, sort of like kinetic into potential and back again and so forth. Turns out that there's a bit of application of conservation of energy here, that same principle, when you're talking about moving charges, and I can even add a little bit here, in E fields. So let's go ahead and add that to the title as well. So conservation of energy of charges that move in electric fields. So the problem with the setup sort of looks something like this here, and you might seen this maybe in your textbook or something like that. But what we'll do is a system like this here. We'll say that we have two plates here, and this plate over here just has a little hole drilled in the center of it, but otherwise it's a full metal plate just like the other one is here. And what we're going to do is we're going to have a little charge here, maybe a positive charge, that gets injected into this plate region with some speed v. So see, it already has some kinetic energy. And what we'll do also is we'll connect these two plates to a battery here. Let's say maybe something like a 100-volt battery. Here's the negative terminal, here's the positive terminal. We'll sort of hook them up like this and like this. So what happens now is this plate gets filled with a bunch of negative charges because it's connected to the negative terminal, and this plate gets filled with a bunch of positive charges because it's connected to the positive terminal. So what we really have, once again, is a parallel plate capacitor turned on its side. As you might be noting from the last couple of videos, parallel plate capacitors with protons are very convenient models to use for studying these issues dealing with charges moving around. So there's a big electric field in here that looks something like this, going on like this, and the electric field lines, of course, all point this way, out of positive into negative. And what we're doing is we're injecting a charge in there. And so there's all kinds of sort of questions you can ask about the system now. That has to do with the motion of the charge and conservation of energy, and that's what we'd like to talk about in this video here. We'll just sort of move off to the side and talk about this here because we have this nice column of space over here. So what we do here, what we have here is then something like this. Well, suppose we want to know what the speed of the particle will be by the time it reaches this plate. Okay, so we could ask that question, and what we know is that this plate over here is sort of at 0 volts because it's connected to the negative of the battery, and this side over here is sort of at 100 volts because it's connected to the positive side of the battery. So what we have is we have this charge here which is going from 0 volts to 100 volts. How would its speed change? Now, how do you know the speed would change at all? Well, you can see that it's moving, its positive charge here is moving opposite to some electric field lines, and we know that F is equal to QE. So as long as this charge is in an electric field, it's going to have a force acting on it. In this case, the force will be opposite to the velocity. So everywhere the charge is in there, so long as the velocity keeps moving this way, the force is going to be that way. So yeah, it'll slow down just on that premise alone. But it turns out we can use conservation of energy to actually calculate what that slowdown would be, and it would look like this. Suppose this is the initial configuration of the charge here. We can say, well, its initial kinetic energy, 1/2 mv squared, is sort of what's driving the whole thing. And by the time it makes it all the way over to here, what does it have? Well, it's going to have another type of potential energy, 1/2 mv, let's say v final squared, because it has lost it, so maybe we can label this one initial over here, because it's going to be a different potential energy. Kinetic energy, the speed's going to change. But what about the potential energy at this point right here? Does it have some or what? We say, yeah, it does have potential energy, because as we discussed in a previous video, here's a positive charge now. It's not really easy to see that this is positive. Here's a positive charge now that's being compressed all the way up against this positive plate, and maybe it's even held there, or for the moment that it's there, it's actually storing some energy because it's near this positive charge and would very much like to get away from it. So yeah, it will have potential energy. But the question is how much potential energy does it have? Well, we have a relation between potential energy and volts, if you recall. This charge now has gone from 0 volts to 100 volts, and if you remember, so maybe go over here to rehash the equations a bit here, we know that the change in potential energy is equal to the amount of charge times the change in its potential. So the amount of potential energy it's going to have over here is going to be plus Q, and the delta V that's gone through is that full 100 volts. And so we're not going to do any more with this equation here, but I'm just showing you, here's the conservation of energy. The initial energy here, which is all kinetic as it enters the plate region over here, has gone into some final kinetic energy all the way over here, but now the charge has picked up some electric potential energy, which is always charge times volts, so Q times 100 volts over there. That's how much energy it has. Another question you might ask is how fast is it going when it reaches this midpoint right here? Same type of conservation of energy. 1/2 mv initial squared is 1/2 mv final squared, plus the potential energy you'd have right here at the center point is going to be a Q, and guess what the potential is right here at the midpoint between 0 and 100 volts. If you guess 50, you'd be right. 50 volts, something like that. That would be a way of calculating, if you knew again that initial entry speed, say this is V sub I, what the speed would be at the midpoint region. So there's another example of energy. What about if the electric field is so strong, it could happen that the charge gets injected like this, slows down, and stops, and then turns back around again. That could happen. Let's see if we could figure out maybe that would happen. Well, we still have that initial energy, 1/2 mv initial squared, and now stopping means the velocity is zero, so we're not going to have any kinetic energy. So we'll say, where would that kinetic energy be zero? But what we also know is that it's going to have it still has some electric potential energy, because we know it's going to move sort of toward the right over here. It's going to be somewhere in this field region here, perhaps not all the way up against the positive plate, but definitely away from the negative plate. So we'll have some electric potential energy in there, and we'll just call that QV in there. And so what you could do, if you know the initial energy, you could actually solve for the voltage the object might have when it comes to a stop. You actually get some number for that. Like, for instance, well, we know 100 volts here and zeros over here. Maybe it's going to stop at 65 volts or something like that. And because you know there's sort of a linear increase between voltage that goes across like that, you could figure out, given that it's 0 to 100, if you knew the plate spacing over here was something like, I don't know, some plate spacing of d or something like that, you could make it correspond with actually what position the particle has when it reaches 65 volts. So it won't quite be at the halfway point. It'll be, 65% of the way over this distance d. So if you wanted the stopping distance right here, let's just say, maybe we call it x here, it's going to be 0.65 times d. 65% of the distance is where it's going to stop. There's another kind of expression, though, for the potential energy of a charge that we covered in a previous video when we were contrasting electric potential energy and gravity. In particular, it was that the change in potential energy of an object as it moves through an electric field is also just QE times x, or charge times electric field times the distance over which it moves. So that's another way actually of setting up this problem here. So you could say 1/2 mv initial squared is equal to 0. Again, where's it going to stop? But you could say plus QE times x. So if you know what the electric field is between the two parallel plates, you can calculate the stopping distance that way also. And remember, these are two parallel plates, so the electric field is going to be sigma over epsilon naught, something like that. So there's just a bunch of relationships that you can deal with in here, but what we've sort of done in this video as a nutshell here is we use the relation that energy is equal, the change in the charge's potential energy is equal to its charge times its change in its electric potential. We sort of use that relation right here. We've also used the other one that we contrasted with gravity here. That change in potential is also charge times electric field times the distance moved in the electric field. And remember that all of these energies here are just in joules. They are just energies. So you are free to combine them with any other type of energy that you're aware of here. And in particular, we combine it with kinetic energy, which is 1/2 mv squared. But I hope you see that what we sort of did in the totality of this video here, in forming some ideas with energy here, is we just use conservation of energy. Like, both of these sides here are all E initial, and this side over here is E final. And everything to the right of to the left of this red line is all initial energy. Everything to the right are all the final energies, all the way down here. So we just sort of use conservation of energy to answer these questions. But we needed a way of getting our electrical entities, in particular the charge and the voltages, into energy. But of course, they just come from these key equations right here.